and science. Good afternoon, everyone. My name is Zhengwei, and I'm a doctor of Professor Chiral. And it's my pleasure today to give you my presentation. My research topic is first principle simulation of order in condensed matter. This is the contents. What is chiral? An object is defined to be chiral when it cannot be superimposed to its mirror image. Chirality is a universal scientific reaching in nature, and it has a significant impact on our lives. For example, for the solid light, its RSI is a drug. Can you speak louder? Yeah, I can define what the duration to you. So you can take louder, but also I can speak like maybe I think it's easier to do it this way. Maybe it's easier and then if I sit here, I can't undo the it doesn't. Its asthma is a drug. Its asthma is deformative. And for crystals, a crystal is defined to be chiral when it lacks both mirror symmetry, inversion symmetry, and rotor-reflection symmetries. It can be classified by its Swiss groups. The German mathematician Thorne has enumerated 65 Swiss groups, and the crystals in these groups all have chiral crystal lattice. Besides the chiral lattice structure, crystals can also have chiral electronic structure. For example, email metals. So they are furnished either right-handed or right-handed chirality. And in experience, the electron spin forms a vertex pattern. And in multiple effect, there are chiral exit electrons move unidirectionally along the edge. Chirality. This was defined when it lacks both these symmetries. And there is a chiral space group, and it is defined by a mathematician formula. Yes, it has some mathematics. Yes. In this group, this is chiral. You mean the relation between the chiral order and the atomic coordinate? Oh, okay,
So you have to all the applications for CHE.
Molecule. Because each service are different molecules. We've got to be superimposed to this mirroring in this Chiral. Increase loss is some of these yes. Yes.
This is the part
And the paralysis will also implement influences in electronic structure. This is a toy model. Suppose this is a box and one electron is in it. We know that it should be a stationary beam. It is a superposition of two waves. One is exponential IPZ and another is exponential minus IPZ. One is forward propagation and one is backward. And if we twist the results, there should be an additional phase shift because of the boundary conditions. For the forward propagation case, the phase shift is exponential IL phi, and for the backward propagation case, it is exponential minus L phi. L is its orbital angular momentum. It is not there in the real materials. This is the band structure of the crystal selenium. It is a Chiral crystal. We can see that for its orbital angular momentum along the gamma z direction and the gamma minus z direction, it is reversed. There is an angular momentum and a momentum altering effect. And the paralysis has chirality material. Materials has drawn much more attention in previous several years, and most research focus on the study of its chiralitis order. However, there are some cases where the pure electronic system can exhibit Chiral order. For example, in the schematic, the blue steps is the charge accumulation. We can see that from the top to the bottom, it forms a vertex pattern, even with the Chiral lattice order. And the Condensed provides an ideal platform to study Chiral electronic order because when charge-density transition occurs, it usually accompanied by a charge-density distribution as well as symmetry weakens, which may introduce additional Chiral order. And then I should introduce what is the charge-density width. This is the most classical model called the Pierce model. It's a one-dimensional atomic chains. And this is its energy band. The electrons are half filled, and its Fermi surface ranges from the minus TF to TF. Suppose we give it an external stimulation with an external field, then the charge density should redistribute according in response to the stimulation according to the linear response theory. And the chi is the response function. We can see that the chi divided at Q equals to Pf means that this system is unstable. It should go through a phase transition. After phase transition, it goes into the charge density phase. And there are four universal features for the charge density phases. The first one is metal insulator transition. We can see that before phase transition, it is a metal without energy gap. And after transition, energy gap opens. It becomes an insulator. The second is lattice distortion. We can see that the ions are distorted. It is dimerized and become pairs and pairs. The third one is charge density redistribution. The charge redistributes, and this is the reason why it is called the charge density waves. The fourth is yes, this is no. The field is like some natural fluctuations in materials. There are some charge density fluctuations which may introduce some external fields. And it is divergent, so it is. I mean, this is an ideal model, and we introduced this model because it is unstable. Usually in our experiments, we see this phase. This is the charge density waves. So it's unstable because we don't want to be yes, it is field. And usually it also accompanies soft photons. It was pointed out by Core and called the Core anomaly. And my research topic is the term order in charge density waves. As I have mentioned before, there are some materials that have intrinsic lattice order, such as tellurium, and there are also some other materials. They are not Chiral itself, but it can become Chiral with the help of charge density wave transitions, like TSE2 and TS2. Charge density waves. Yes. I will study their Chiral lattice order and Chiral charge density wave order. Study their Chiral phenomena and their chirality manipulations. In addition, I will also introduce a bit about TIT2. It's not related to the Chiral order, but charge density wave material. And is methodology. I use density functional theories here. Density functional theory is a realization of first principles calculations. What is first principles calculations? It means that we can start from some basic physical quantities such as the loss of the light, the elementary charge, the mass of the electrons, and the Planck constant, and so on, without any empirical parameters. And utilizing the quantum mechanics, we can get the many-body wave functions and get everything we want. But there is a problem that the computational cost is very large. For example, for a single electron, we need m by m by m is m cubic with to describe its wave functions. And then for n electrons, the degrees of freedom becomes m to the power of 3n. It increases exponentially. Degrees are one. For example, I use 100 to describe the wave function on one dimension here. Even for 10 electrons, the computational cost is far beyond the current capacity of modern computers. So people need to do some simplifications. And in 1964, Hornberg and Cohen established the HT theorem. The first theorem says that the ground state electron density have a one-to-one correspondence with its external field, and hence determines all the physical properties of the system. And the second theorem states that the total energy E is functional of the charge density rho. And by minimizing the total energy, we can get its ground state charge electron density. The HT theorem simplifies many wave function problem into a charge density problem. And 1 year later, Cohen and Chan established the Cohen-Chan equations. It is a realization of HT theorem. It uses an auxiliary non-interacting electron system to substitute the real many-body electron system. And in the auxiliary system, it is under the Cohen-Chan potential, and the auxiliary system reproduces the same ground state charge density as the real systems. In this auxiliary system, the exchange and the correlation, the interactions are all discarded into the V-excitator. The quantum equation successfully reduced the problem of many-body wave functions of the order of an exponential order to the problem of charge densities with cubic order. It is very efficient, and the density functional theory has already been implemented in code like RASFAM and QE. It is now widely used in the research of electronic structure of materials, surface and interface chemistry, superconductivity, and photon spectrums. Although density functional theory is very efficient, it still has some limitations. For example, it cannot study the systems out of the ground state. So in 1984, Wunsch and Gross come up with the Wunsch-Gross theorem. It says that there is a one-to-one correspondence between the charge density rho and the external field V. And at the end of the last century, Newman realized the equivalent quantum equation in the time domain. It also used a non-interacting auxiliary system to substitute the real system, but it can reproduce the same charge density as the real system. And the charge density can be solved by the time-dependent quantum equations. Now, the TDMT theory has also been implemented in code, and Octopus is the first one, and I think it may be the most famous one. In my PhD group, we have our self-developed package called TDEP, and my later calculations are based on TDEP. GDP theory has advantages in the area of linear and nonlinear optical response, ultra-fast electron dynamics, charge and energy transfer processes, and strong field physics, and so on. That is my research. My first work is to study the Chiral charge density waves in TISE2. Previously, there are some experimental detections to study the coupling between the chiral order and the charge order. For example, in TAS2, it has the authors found that it has a chiral charge density beam superlattice, and it is coupled to a chiral electronic structure. You can see that it is Vanderbilt shape. And in TSE2, in this work, the author did the Fourier transformation for this STM image and found that its intrinsic rotation symmetry is broken, and this diffraction pattern can be either clockwise or anti-clockwise sequence. It is a Chiral charge order. And in its X-ray diffraction studies, the authors found an anomalous diffraction peak implies the emergence of chiral lattice order. And besides the chirality detections, there are also some chirality manipulations. In TSE2, the author used circularly polarized light to manipulate, to train and probe the sample, and they observed the circularly photogalvanic effect. It means that the system, there is a chiral charge order. But in theory, the charge density of TISE2 is a chiral, so it's detailed microscopic mechanisms is still unclear, so we conducted our research. This is the crystal structure of TISE2. It has a layered structure, and different layers are coupled together by van der Waals interactions. And for unit cell, we calculate its phonon spectrum. We can see that at the end there is a huge soft phonon mode. It corresponds to charge density super structure with double periodicity. Due to its rotational symmetry, so the following mode is that if the analysis structure is distorted along these distribution vectors, I mean the following mode, its energy is minus, it will be stabilized. So its initial structure is not stable. It should be distorted along this direction. And due to its rotational symmetry, it has three equivalent endpoints, M1, M2, and M3. And here we calculate the phonon mode for all these three endpoints. It's in the figure. They are also symmetry equivalent, and because they are emitted by a single endpoint, it is called the single Q mode. And if we superimpose these three single Q modes together, we can get this pattern. It is called the triple Q mode. It is irreducible, and it is thought to be the ground state in experiments. But the single Q mode is a metastable mode, and it is barely studied in previous research. And in our study, we try to induce such a single Q mode. A speed player is triple Q mode. It's a definition of yes. A straightforward idea is to use a linearly polarized light because the polarization will break the intrinsic symmetries of the material. and upon excitation, I calculate its binding strength. We can see that the covalent bonds are weakened by the excitation. And these three different curves is boundary strength along three different directions. We can see that the bounding strengths along M2 and M3 direction are weakened by about 9%, while that along the M1 direction is weakened by about 5%. So there is an anisotropic bond order. There should be a single Q charge order. It is more clear in the residual densities. We calculate its excitation number in the first Brillouin zone. We can see that more electrons are excited along the gamma M2 and the gamma M3 path, while little is excited along the gamma M1 path. So, by linearly polarized light, we successfully excited the single Q charge order. It is a transit state, and it's the electron subsystem will interact with the phonon subsystem via the electron-phonon couplings. Then we study its phonon subsystem. This is its potential energy surface. The black curve is potential energy surface for the ground state, and the current curve is for the excited state. We can see that after excitation, its potential energy surface is degenerated. The potential energy surface along the M1 direction still is a double wheel shape, while that along the M2 and the M3 directions becomes a single wheel. And the structure, the crystal structure, should be trapped in the energy minimum. And should be a single Q mode along the M1 direction. It is more obvious by projecting the line movements onto each phonon mode. We can see that the M1 mode is significantly excited, while the M2 and M3 modes are hardly excited. So by excitation, we successfully get a single Q charge order as well as a single Q lattice order. And then it is straightforward to deduce that by circularly polarized light, we can induce Chiral phase in the bulk because different slices undergoes experience different electric because different slices undergoes electric field along different directions. Then we need to study its dynamic stability. But this system is too large to calculate, so we use a simplified three-layer model. This is Q1, Q2, and Q3 patterns stacked in sequence. We calculate its dynamic stability. We can estimate its excitation intensity by the Fermi-Dirac distribution. And we calculate its phonon spectrum under different excitation intensities. And for the integral, we can see that under very weak excitations, it has a huge soft phonon mode, so it is unstable. And for the red curve, with strong excitations, the soft phonons hardens and it becomes dynamic stable. We also calculate the Chiral charge density order and its soft phonon frequencies with different excitation intensities. We can see that the yellow shaded area, the Chiral charge density configuration is stabilized. and the soft photon mode disappears, means that a circularly polarized light we can draw a conclusion that a circularly polarized light can successfully induce and stabilize Chiral phase in TISE2 charge density waves. We also calculated some experimental predictions, such as its circular photogalvanic effect, the circular dichroism, and electron diffraction patterns. And last year, I see some other experimental research. They do very similar research as mine and get some observations. In another material, RPV3SP5, the author used linearly polarized light to illuminate the sample. And they can see that the single beam order is either weakened or enhanced. By this means, the chirality can be switched. I think there may be the similar mechanisms as that in TISE2. And another work is also in TISE2. The author used a pulse to excite the samples and find some one-dimensional domain walls. I think it may be a verification of the single Q mode. Here is a brief summary. We verified the single Q and the triple Q charge order. We found some laser induced single Q free transition. We propose a Chiral phase transition that is induced by circularly polarized light, and we did some experimental predictions. The second work is about the manipulating chirality in charge density material TAS2. In previous experimental research, there are usually two methods to manipulate the chirality in charge density waves. One is by electric field. In NBFE2, the gland area and the goal area are domains with different chirality. And by encoding an electric field, it's also found that the domains is reversed. This chirality is reversed, and the domains is shifted. Another method is by magnetic field in PV3SP5. We can see that initially there is an clockwise charge density waves, and by encoding a magnetic field, the chirality is reversed. This is because there are some couplings between its electronic structure and the magnetic field. This is my collaboration work with experimentalists. My collaborators use Chiral Raman spectroscopy to characterize the TAS2 charge density phase. They find some Chiral signals. It implies that this charge density wave is Chiral. And its Chiral is easy to understand because its charge density wave superlattice in two-dimensional is either in this shape or this shape. Its mirror reflection, its mirror symmetry is broken. We call them alpha or beta phase or left-hand or right-handed phase. What is interesting is that my collaborators she stack two obligate chirality flakes vertically like this, and do annealing to this sample. And after annealing, we found that at the overlapped area, the initial obligate chirality homostructure now transformed into the same chirality homostructure. We call this the chirality locking effect. I give it an theoretic explanation. For the Condensed view, superlattice of PS2 for its different stacking orders, for its dimerization or not. For orbit and the thin parallelity stackings, I construct a series of initial structures and calculate its dynamic stability. It can be defined by the body energy. The higher the body energy is, the more stable the energy is. And we can see that for the alpha and the beta beta, it means the similarity stackings is body energy is higher. It means that the system has lower energy, so it is more stable. This is the reason of the parallelity locking effect. And to make it more clear, I calculate the radial distribution functions. The radial distribution functions is the probability of finding a particle at a specific distance compared to a reference particle. We can see that for the Bohr curve, it is thin parallelity stacking. It is a series of discrete peaks. It is more well ordered, and it means that it has less entropy and more energy flow. But for the opposite parallelity stacking, as shown by the pink curve, it is messy and is more energy unfavorable. And as shown by the red arrows, some ion pairs are too close. This should cause a huge Coulomb repulsion, making it unstable. Yes, because some ion pairs are very close. Yes. And here is a brief summary. We visualize with the calculation with the experimentalists. We visualize the Condensed waves. We manipulate the order in Condensed waves with those structures. We propose the interior parallelity locking effect, and we attribute the microscopic mechanism of parallelity locking effect to the interior interactions. Here are some other works. Due to the thermal fusion and my speaking speed is very slow, I would only introduce some other works briefly. In this work, I studied Chiral crystal tellurium to study its Chiral responses and chirality manipulation. And another work is Morial against Condensed waves. It is also an experimental calibration work. My calculators construct PIT2 and the PISE2 heterostructure. Usually the Condensed wave is for PIT2 is very weak and it only occurs at very low temperatures. But in their case, the Condensed wave can occur 10 times even up to the room temperature. And using density functional theory equations, I found that because of the lattice parameter mismatch, there is a Morial pattern in the TIT2. And in the Morial superlattice, there are local strings. It is the local strings that significantly enhance the Condensed wave in transitions. I think it is inspiring for future Morial engineering. And here is a summary. We investigated completely induce the single-pure matter stable mode and the Chiral mode. They reveal the interior erratic logic that the in-charge stable homostructures T2, and we investigate more real-enhanced high-density transitions in two-dimensional materials. And the acknowledgement Professor Lu and Professor Wang are my supervisors. They are both very excellent researchers. Professor Li, Professor Tong, and Professor Li are my experimental collaborators. They have very advanced equipment, and I learn a lot from them. And Dr. Chen is my groupmate, and he helped me a lot in the past few years. Here are my groupmates, and many thanks to them. Thank you for your attention. It can be destroyed by temperature, and it can be stabilized by deflections. Yes, it can be harmed by deflections. Scenario magic is if we snap two different materials together because their lattice parameters are different, are slightly different, and to make it match, we should construct, there should be a very huge super lattice to make it
so it would be like a differentiation
Yes, for the fundamental say this guy is it's hard to take into the temperature into consideration, but usually people can choose the occupation number of the atmospheric from the direct distribution. It can partially substitute the temperature effect.
I assume that you are from this it's only one diagnosis where you don't have access to exact evidence to be.
TFT is beyond the bound state.